So thank you. I'm now very distracted by the previous speaker. I'm thinking about projection effects, and I have a paper draft here written with Glenn van de Ven, and I opened and I read through the math that we did to see if it's consistent with your work or not. But I'm supposed to give a talk now about spectroscopy. But yeah, a little bit distracted now. In any case, I'm very happy to be here at this meeting now. I've been planning to come here for many years, and there's always something that came up. Being from Europe, it's kind of far away, Santa Cruz, so it's always a bit complicated, but I'm very happy to finally now make it here. I'm at Ghent University now, which is very far away from here, so just a couple of things about Ghent. It looks very impressive. This rivals Cambridge in beauty. It's surprising how many people haven't heard of it, and especially in the astronomy world, not many people in galaxy evolution have heard of it, because I'm basically the first one doing galaxy evolution there. It's in the northwestern part of Flanders, as you see at the bottom right there, and hopefully you'll hear a lot more of from us over the next few years. So LEGA-C. It's a very large survey at the VLT, with the VMOS instrument, which is no longer on the telescope. We spent more than 100 nights observing there, taking 20-hour deep integrations of several thousand redshift 1 galaxies. And the goal of that exercise is to get high signal-to-noise spectra in the rest frame optical at a fairly high resolution. Not high resolution for a stellar person, but as high as you need for any galaxy stuff. We did the DR2 last year, and those data are all publicly available. All the raw data is publicly available immediately. So if you want, I don't recommend it. You can download it and reduce it yourself. No, but we put a lot of effort in that, so you don't have to do that. The LEGA-C collaboration, who are we? There's a group of us, the LEGA-C group. It's between Heidelberg, where I was previously, and now Ghent. There's 8 of us, and then there's the wider LEGA-C collaboration. Many names will look familiar to you here. So what does the sample look like? I mentioned it's more than 3,000 galaxies redshift 1. This is the stellar mass range we're looking at, above 10 to the 10th. And this is the star formation rate distribution. All we do is a redshift selection, 0.6 to 1, and a K-band magnitude selection. It's completely blind to color, morphology, or anything else. So this is what you get then. You get this galaxies on the star forming sequence. And the passive galaxies down here. It's color-coded with emission line signal-to-noise, just the signal-to-noise of the brightest emission line, just to indicate that all these galaxies have emission lines, and half of the galaxies down here have emission lines, but they're fainter. So why do we spend more than 100 nights trying to collect these data? That's the next slide. The basic data product is these 1D extracted spectra. Here's an example of a passive galaxy. This is the observed wavelength range, to understand the complications of reducing these data. A passive galaxy with strong absorption features and no emission lines, so there's some weak O2 here. And here's a star-forming galaxy, where you also see absorption features and the emission feature. So the first step we take is we decompose this spectrum into a stellar continuum component and a emission line component. More on that later. Okay, so why do this? The driving questions, you better be general in your science goals if you ask for more than 100 nights of observing time, right? So how do galaxies form? And no matter how you try to answer this question, you always run into this question of why do galaxies stop forming stars and become quiescent? Now, there's 2 things that LEGA-C provides that makes it different from anything else, and that we have access to the stellar populations at a high resolution, and stellar dynamics. Especially the stellar dynamics part is completely new at this high redshift. Not completely new. There's a few dozen massive ellipticals that have been analyzed before, and a handful of lensed galaxies at redshift 2, Andy Newman and others. Now we want to combine this with everything we've learned about the structural evolution of galaxies from candles and 3D HST, and we want to connect it with the gas and ongoing star formation. So that's the tools we use to answer those questions. Now I'm going to go very quick now and flash many results that we've been working on. I don't recommend that that junior people give a talk like this, showing too much, because I've learned from Hans Walter Rix that people will remember 0 or 1 thing from your talk. So this is completely the opposite, right? So I leave Heidelberg and it completely falls apart. Good. So here's the passive galaxy spectrum we showed earlier. And the first thing you can look at to summarize its general character is the so-called D4000 break, the flux ratio between this part and this part, and the strength of the H delta feature. So old galaxies will have a weak H delta absorption and a strong break, and young galaxies the opposite. So this is a canonical diagram introduced by Guinevere Kaufman 15 years ago from the Sloan survey, where you plot this Balmer line absorption strength against this D4000, and the Sloan population matched to the LEGA-C population in terms of stellar mass looks like this contour. So the strong peak at old age and a tail towards younger ages. Now the LEGA-C population, a mass-matched sample, looks very different. The peak of old galaxies is shifted. That's just the age of the universe, right? Galaxies cannot be this old at redshift 1. Plus there's a second peak here now, which means that the populations of the star-forming galaxies are actually overall young. The Milky Way would be somewhere here. It is star-forming, but it's not overall young, right? So one conclusion we drew from this work, and there's a lot more in this paper, is that 50% of the massive galaxies at redshift 1 are still in the middle of their main formation phase. As I said, I'm going to go very quick. We made this diagram and we cross-matched against the 3 gigahertz VLA data set. So this is a little side project. But we noticed that all the radio galaxies, the radio AGN, are in the bottom right corner. What is new about this is that we knew that radio galaxies happen in red galaxies at high redshift, but not that they're this old. The lifetime of a radio galaxy is a few hundred megayears, but these galaxies have been quiescent, not formed any stars, for several gigayears. So it's not that these radio jets quench the galaxy or anything. If anything, they maintain quiescence, but there's no immediate step from you make a radio jet and you quench a galaxy. And very quick. This made us look at, one thing we noticed is that all these radio galaxies are perfectly round. Most galaxies are not round, right? They're flattened. Why are these all round? So we went to Sloan to have more galaxies, and we constructed a sample of 3,000 radio galaxies at redshift 0.1. So we started by plotting the radio-loud fraction of quiescent galaxies in red and star-forming galaxies in blue as a function of the stellar velocity dispersion, also known as the black hole mass. So you see this 3 order of magnitude increase in radio-loud fraction from low velocity dispersion to very high. Somehow there's no difference between the quiescent galaxies and star-forming galaxies. Interesting, but that's not what this is about. But now, about the roundness. So here we have the projected axis ratio for galaxies in this sigma bin, here, only the quiescent galaxies. And the radio-loud fraction depends very strongly on the projected axis ratio. This is really strange. Why are flat galaxies not radio galaxies? I have no answer to that question. I have potential answers, but this is something we noticed and we wrote up in this paper this year. And I just wonder what this means for maintenance mode feedback via radio AGN. Back to LEGA-C. These spectra, of course, demands that you do more than measure D4000 and H delta, right? That's not why we took 20-hour integrations. So we built more advanced stellar population models. We used Charlie's FSPS code here to reconstruct the star formation histories of hundreds of galaxies. So here's an example of a very young galaxy. You see all the strong Balmer lines. And this is the star formation history in terms of star formation rate as a function of the age of the universe. It stops here because that's where we observe the galaxy at redshift 0.8. So this is an example of a very young galaxy with a mass-weighted age of 1 gigayear. Here's 6 more examples. There are 3 young galaxies on the left and 3 old galaxies on the right. And one thing we understood from these fits is that galaxies have very long memories, that their current star formation activity is very strongly correlated with the star formation activity it had many gigayears prior. That's one thing we learned from this. You also see here this galaxy with the second blip here. You can call that rejuvenation. So we looked at that in more detail in a paper this year. Here's two examples of galaxies that had a peak of star formation early on in the universe. It went quiescent for some time and then had another blip. So I identified a few dozen of these galaxies in LEGA-C. They're typically sitting in what you might call the green valley in the color mass diagram. And yeah, these secondary bursts typically contribute 10% of the total stellar mass, and it happens to about 15% of the full galaxy sample. Yeah, so that's what this says. 15 to 20% of quiescent galaxies at the LEGA-C redshift, 0.8, have a rejuvenation epoch in this redshift range. It doesn't add much stellar mass typically, but it is something. Okay, so I need to go even faster. Has it been 10 minutes? 5 minutes. Have I been talking for 15 minutes? Can somebody verify that? I have a hard time believing that. I have a 23-minute talk, right?
20-minute talk.
Okay, good. So with these spectral fits, we basically reconstruct the intrinsic stellar spectrum, right? It's free of dust. With the photometry, you see the stellar light with the dust. So the difference between the two is the attenuation. So here we have the intrinsic stellar spectrum with synthesized photometry and compared with the observed photometry. So here you see a difference, and that's due to dust. So from this we reconstruct attenuation curves, A lambda as a function of wavelength. We did this for all the star-forming galaxies, and you see, well, galaxies with different amounts of dust and different so-called UV bump strengths. I'm not going to explain what it is. You already know it or you don't. So, as you might expect, this is stellar mass. Sorry, I'll just show this one. Stellar mass versus axis ratio, the overall attenuation at 4,500 angstroms. Obviously, the edge-on galaxies have more attenuation than the phase-on galaxies. That's what you might expect. It's nice to see it this way. And more massive galaxies have more attenuation than low-mass galaxies, even when seen phase-on. This is new, I think. There's the bump strength. The 2175 bump strength is highest for fairly low-mass galaxies that are seen phase-on. This makes sense in the context of the idea that this bump is associated with PAH features around star-forming regions, which you can see in phase-on galaxies. The mass dependence I don't understand, but this is, I think, the best attenuation characterization we have so far at high redshift. Quenching. So here's the size-mass diagram we've been talking about a lot the past few years. For passive galaxies, color-coded with the H-delta strength. So young is orange and dark purple is old. We're going to smooth this a little bit to reveal the trends we think we see. And you see that old galaxies are here at high mass, young galaxies are large size and lower mass, and then there's a little bit of young galaxies here. Now this makes sense. These are basically galaxies, star-forming galaxies that somehow run out of gas. Nothing dramatic happens. The star-forming disk fades, and you have a young, large, new passive galaxy. These are different. Now this does reconcile two results we've seen in the literature over the past few years. I won't go in detail here, but this sounds contradictory, but the fact that we see young galaxies here and here unifies these two results. Talk to me if you want to know more. So about these recently quenched galaxies, in this U minus V versus V minus J diagram, they sit over here. These are spectroscopically selected now. And the question is, how does this what can we learn about the star formation histories of these galaxies? So what we think we've learned is that the smaller their size, the bluer they are, and this is consistent with a scenario in which these galaxies experienced a central starburst of varying strength, which regulates this color and the size with roughly these parameters. Short bursts about a gigayear ago that add 10 to more than 100% of the pre-existing mass. If this is true, you should see a negative age gradient, a positive age gradient, younger centers. So that's what we looked at with LEGA-C, which is a slit survey. We tried to extract the spectra 10 kiloparsec away from the center, so it looks noisier, compared to the center. We do this for many galaxies, and we compare them, and we see the following. For post-starburst galaxies, these recently quenched galaxies, we see indeed that the H delta gets weaker toward the outskirts, and for the control sample of passive galaxies, it slightly goes up. Here's an iron index to figure out if this is an H or a metallicity gradient, and as much as we can tell, it's fairly low signal to noise still. Quiescent galaxies in general have negative H/metallicity gradients, but these recently quenched galaxies, which we argued have central starbursts, have positive H gradients, consistent with that idea, independent evidence. Okay, the second topic of my talk is stellar dynamics. So the obvious number to measure first is the stellar velocity dispersion. When you measure the velocity dispersion, you want to put that in the Weber-Jackson relation, and we see a very tight one, 0.1 Dex intrinsic scatter. Regardless of whether the galaxy has an emission line, is star forming or not, it's all 0.1 Dex scatter. If you compare the gas dynamics with the stellar dynamics, interesting things happen. So this is the ionized gas kinematics velocity dispersion divided by the stellar velocity dispersion. That's a function of stellar velocity dispersion. It's flat. That's good. There's some scatter, 0.15 Dex. Now if you replace the x-axis, if you switch the x-axis around, you see a trend. So if you see a galaxy with a low gas dispersion, it means you probably are underestimating the stellar velocity dispersion, and vice versa. No time to go into this. This part I understand, this part I don't. Spatially resolved kinematics, this was previously was integrated measurements. This is again our slit. Here's an HST picture. So we extract the kinematics along these slits, and you see the rotation curves from the gas and the stars, and the velocity dispersion curves of the gas and the stars. This is a typical star-forming galaxy. So we measured these rotation curves from massive passive galaxies here. And the first thing we did is we compared with CALIFA, a local IFU survey. We mistreat the CALIFA data, convolving it with a giant seeing beam to mimic the LEGA-C data. And this is the observed V over sigmas we would have seen for the CALIFA galaxies. So that's the velocity measured at 5 kiloparsec divided by the central velocity dispersion. And we compared it with LEGA-C, and we see a lot more rotation in LEGA-C. And the conclusion we draw is that the quiescent galaxies have significantly slowed down in rotation, and we can attribute that to dry merging. Now you want to do a bit more than just making these measurements because they're so strongly convolved. So we built Jeans models where we look at VRMS, sigma squared plus V squared, again along the slit. And we built Jeans models with 4 free parameters, basically the mass and the inclination and the anisotropy. No time to go into this. And that's what we get. So come find me if you want to know more about this. So we did this for hundreds of galaxies, star-forming, passive, everything. And it all looks quite good. So here is this V5 over sigma 0 again, but now for the Jeans model and not the observed one. So this is basically seeing corrected for inclination, not corrected for inclination, but corrected for the slit geometry. As a function of stellar mass, color-coded with specific star formation rate. So 2 things. There's a strong correlation between V over sigma and star formation state at a given stellar mass, and the trend with stellar mass is not very strong. The star-forming galaxies are almost all up here. The passive galaxies have a very broad range in V over sigma. One other way to look at this is V over sigma is now here versus the K rotation parameter. All you need to know about this for now is that if K is 1, then the flattening of the galaxy that you see can be entirely attributed to rotation, or you're looking at a rotationally flattened system. And it's good that that's apparently what's happening. So most of the star-forming galaxies have K as 1, so they're rotationally supported disk systems with high V over sigma, which means they're highly flattened. About half of the passive galaxies are also K as 1, but with lower V over sigma, so they're thicker systems. They're rotationally supported, but they're thicker. And then there's this flurry of galaxies here, where they have some sort of geometry that is not explained by flattening due to rotation. So this is the first time we see this connection beyond the local universe between the stellar dynamical state of a galaxy and the star formation activity. Of course, the next step is to connect this stuff to the entire star formation history. So far, this has been separate efforts within the collaboration. Now we're going to put it all together. Did you do that? Okay, no, but I'm done. That was the, I don't know why I didn't go to the conclusion slide. So I'll just wrap up here. These are the very short answers. We and the whole field, this is not the legacy answer to these questions, right? This is the combination of all our work combined with the legacy work to these central questions that motivated the legacy survey. I realize this was very quick and I still went over time. I apologize, but I'm here all week. Please come talk to me about any of these topics. But we covered a lot of ground. Thank you.
We will get the next speaker, start to get set up, and in the meanwhile, we can take maybe 1 or 2 questions. Michael.
So you said you found quenched galaxies that have star-formation histories that are like they've been rejuvenated sometime in the past. Do you ever find star-forming galaxies that were once quenched, or is that harder to?
That's harder to do. Yeah. We can look at the posteriors in the same way, the posterior star formation histories the same way as we do for the passive galaxies, but I would trust them less because of some systematic effects in the age range between 0 and 500 mega years. Yeah, it's fishy. And if it was quiescent 2 gigayears ago, it would be very hard to tell if it has been star forming ever since, right? The population would be a lot brighter.
Okay. 1 quick question.
They're pretty resistant to changes in metallicity and I mean, to properly answer this question, you need to use a suite of different star population models, allow for different kinds of metallicity variations. But I do believe them because you do see the difference in the spectra themselves, right? I'm kind of old-fashioned like that. If you don't see why something happened in this complicated MC business, if you can't pinpoint that to something in the spectrum, then you're in trouble. But we do see differences between rejuvenated galaxies and other quiescent galaxies with the same H delta absorption strength, for example. You do see subtle differences. Now, the fact that the model makes that the rejuvenation event is another thing, but there is something different about these galaxies. So.
Okay, so let's thank Arjen again. The next speaker is Han An.